That's the overall reaction. If you look at the overall reaction, lithium plus makes lithium plus I have over here. That's not very, that can just be taken away, correct? So it's really just the reaction of cobalt oxide and lithium and graphite makes lithium, cobalt oxide and graphite. Which gives you already an inkling that if you are thinking about this reaction, the concentration of lithium ions in your solution in the electrolyte will not be of very great importance here. The other part which you could have said is, okay, these ones here, these are just delta G's. They're not delta G's under standard conditions. So what you could have also said over here, now this might be something like a standard voltage for this lithium plus cobalt oxide makes lithium cobalt oxide reaction. And then, because this is a delta G naught over minus 1F, and then plus this corrections for that, which is given by the Nernst equation, which I'm going to write over here in a moment. So plus we had here RT over minus 1F, the logarithm. And then on that side, you have the minus over here, and then there's the minus the standard voltage for the lithium plus the graphite makes lithium add graphite, and then that will also contribute something to this RT over minus 1F, the logarithm. Now what do we have as the argument in this logarithm? What do we have from there? Now we have to have a look at the stoichiometric coefficients. So we have to have here a stoichiometric coefficient for lithium of minus 1, or we had one there, for lithium of minus 1, and in order to take care of that one, we would have here then the concentration of lithium plus ions. If we go directly from activity to concentration, then the next thing is here that we have cobalt oxide. We would need to write cobalt oxide down here, but we can't write a concentration for that because the cobalt oxide is in electrodes, it's not in solution, it's not dissolved. So the activity of that cobalt oxide, then we really have to keep it as the activity of the cobalt oxide. Somehow A of cobalt oxide over there. And that probably then has to do with the surface area and the surface roughness of that cobalt oxide, but it is certainly not the concentration. And then for the product, we have lithium cobalt oxide over here, or we have the lithium cobalt oxide from there, doesn't matter. That again is a solid object, so we only have an activity for that solid object. We don't have something like concentrations which would help us describe it in an easily captured numerical value. So the activity of that one, and then we are also needing to do this one here. We see there's a minus sign. A minus sign in front of the logarithm turns around the argument. Minus ln x is the same thing as ln of 1 over x. So we need to flip everything around. This one here should be in the denominator, but because of that minus sign over here, it comes into the numerator. So we have a concentration of the lithium plus here. And then we have a concentration of the graphite, but the graphite again can't be expressed in the concentration. So we can even really only have an activity for that written. And then we have to have now in the denominator the activity of this lithium located at the graphite. Where unsurprisingly you see this one here will cancel. which is the same reason why it had cancelled already here in the delta G of your overall reaction. And you're left with all these activities over here. Activity of graphite, it's an element, correct, in standard state, so activity is probably 1 over here. And all the other activities, you might be saying, oh, they can deviate a little bit from 1 because we make surfaces different and so on, the surface rough, lots of surface area, any of those kinds of things. But that would affect the graphite just as much as the lithium in graphite, and the lithium cobalt oxide just as much as the cobalt oxide, because after all, that's one object before and after. So this term here pretty much goes away, comes very close to 1, the argument of the logarithm. Logarithm of 1 is of course 0, and that term greatly falls away. And the concentration of this is not really much different to what we have in the others. So something like that was that what you could go beyond in your homework, and the TAs will give you some extra points if you realize that. But where you really had to come up with in the homework was this portion over here. And you did that by looking at all those equilibrium, the same kind of equilibrium which I mentioned. Okay, that was a Daniel slide. And so let's ask a question here. What does a negative standard potential imply? This reduction is likely to occur. This half cell is likely to be on the left-hand side. Lots of energy is released in this reduction reaction on that of these ones. Negative standard potential. Okay. This reduction is likely to occur, or this half cell is likely to be on the left-hand side. Even split in this class. Those of you who were no, it is, the reduction is really unlikely to occur. You have a negative reduction potential for something which easily oxidizes, meaning it's not likely to occur in the reduction. So you can see over here, potassium reduction has a very negative potential. It's not likely to be reduced potassium. It's likely to be oxidized, the other way around. Okay. If your cell reaction is negative, what happened? Nothing, that's fine. You mixed up left and right of the cell. The reaction is not reversible. Okay, we have even more reaction than we had a moment ago. Here, to this, let's see, what are your answers? You're mixing up left and right, that's correct. If you get a negative value for the potential of your cell, it just means that you placed on the left-hand side where the reduction takes place and on the right-hand side where the oxidation takes place. And you should just put it the other way around, and then you get a positive. Because you always take right minus left, and if you get a negative number, you should have taken left minus right and get a positive number. Because that is the way this happens. Okay. So, as a reminder, IUPAC representation, oxidation has to be on the left-hand side. Reduction has to be on the right-hand side. Left-hand side is the anode, right-hand side is the cathode, and the voltage, the electromotive force, as the standard the left, and then any corrections from the Nernst equation. Last one. The way we write the Nernst equation, what do you need to maximize to get a big voltage of your cell? The numerator in the logarithm, or the denominator in the logarithm? What do you need to get big? Well, we'll keep it going forward and backward. Let's have a look for that, right? We have a minus sign over here, correct? The minus sign in the Nernst equation, I just mentioned it over here. The minus sign in front of the logarithm flips around the argument inside that. In order to get this value here big, well, the bigger cell is always positive numbers, otherwise you made something wrong. We just established that. So, in order to get this one big over here, and realizing that this one here flips things up, we want to have the denominator getting here big, because the minus sign will flip the denominator into the numerator, and then we get a big value of that. Okay? Okay, that was an expectation. Homework 3, that was the one which you just had to do. The first one, I did that on the board already. Then I asked you, discuss why a Daniel cell is not reversible. Pretty much blank when we talked about that in discussion group yesterday. At least those that talked to us, probably everybody else knew, but there is a question. What does reversible really mean in this context? In this context, reversible means, from a very practical way, you can recharge it. It's that easy. You have a rechargeable battery. You can discharge it, you can recharge it, it's reversible. You drew a zinc carbon battery for homework. Is it rechargeable? No, it's not. You all know that. Once you have your AA battery or AAA battery empty, throw it away. You have a lead acid battery in your car. Is that rechargeable? Yes. You know the generator in your car, you can always put new power into the battery. So that is reversible. So you drew a reversible and a non-reversible battery for homework. So what was the two differences? And how does it relate to this particular Daniel cell? Now, reversible means that if we operate this thing as a galvanic cell, meaning as a battery, or as an electrolytic cell, meaning doing recharge, then exactly the opposite reactions take place. Is this the case in this? Okay. So we first need to figure out then, I guess, what happens in the Daniel cell when we use it as a battery, when we discharge it, when this thing is operating the telegraph and somebody is forcing on the telegraph, making these differences going along the wire. And what happens then is that we have here the zinc, and the zinc goes into the solution, becoming zinc 2+. And the copper, there's copper 2+ ions in the solution. And they plate out, they precipitate, become metal on the surface of the copper. And So we get a smaller concentration of copper ions. That happens predominantly. Why does it happen at all? Because copper is a more noble material than zinc. And as a consequence, copper is holding better to its electrons than zinc. And so electrons are better being part of this copper than being part of this zinc. And so it is energetically favorable. We have a reduction reaction, the reduction of these copper ions here on this hand side. And we have an oxidation over there. We have a redox reaction. And you all know redox reactions where you put the stuff together. I hope somebody did with you, for instance, a reaction of aluminum powder with iron oxide, thermite, showed that you can wonder somewhere where you see molten iron comes out. Lots of heat is released in that, if you do. And you use that reaction, it's technologically useful. If you ever went by railroad, the tracks in the railroad are welded like a thermal reaction. And so to make the rails really warm and have them warm together. Okay. It's a redox reaction going on letting us up. But in this redox reaction, the reduction and the oxidation are separated in space, and the energy released by that redox reaction is not going into heat so much, and it's not going into glowing and emitting light or fire or whatever, but rather the heat for that reaction is as work going through the wire, driving the load. The load might be used up going your start energy, start up in the car, or whatever you power this thing. Okay? Now, reversible. Let's see. Let's still see the battery operation. In the battery operation, zinc is dissolved. What will happen to that zinc? Will it all stay on the left-hand side? It certainly won't, because in this solution of zinc and sulfate, we want to have a balance of how much charge do we have in the zinc ions in the solution and how much charge do we have in the sulfate ions in the solution. And if we have more zinc 2 plus ions than sulfite 2 minus ions on the side, then the zinc will go onto the other hand side. The sulfite might also go this way, but sulfite is a negatively charged ion, so its ovation shell is bigger, so it's much more harder for it to move, so practically the zinc moves. Now if the zinc moves on this side, really my copper electrode is sitting in a solution of copper ions and zinc ions. Doesn't make a difference. The zinc is less noble than copper, so zinc will not do anything. But now let us think about the recharging battery, the reverse reaction. I'm driving voltage, I'm making this really, really positive. The copper says, I wish I could reduce the ions over here, but I have so few electrons in myself, I electrode. I rather have to expel some of my copper ion atoms into the solution as copper ions, keeping the electrons not feeling so positively charged. And so copper ions go into solution trying to recharge, this battery. So the copper ions flow in the solution, then there will be more copper ions than sulfide ions on the side, so we'll drive copper ions on this side. But now we have a problem. Those copper ions, they see there's a zinc rod, and they come over here to the zinc rod, floating against the zinc rod, bumping against the zinc rod, bumping against the zinc electrode. And the electrons will say, hey, I don't want to be a zinc electron, I want to be a copper electron, and I'm much lower in energy, that's much better for me. And so the electrons from the zinc electrode will jump ship and say, oh, I'd rather reduce the copper ion and make it a copper atom being part on the surface of the zinc electrode than staying a zinc electron in the uncomfortable electronic environment of zinc. And so copper plates out on the zinc electrode, and we get and some zinc will go into solution, and we get a copper-plated zinc electrode. No more, at some point there will be no more zinc exposed to the solution, that will convert. So it is not reversible. Something really bad happened. Same thing, something really bad will happen with your zinc carbon battery, AA battery, or something. You try to recharge something really bad that might not be contained by the metal can. So, reversible cells supports the same reaction during charging and discharging. Strictly speaking, thermodynamics only applies to reversible cells. Thermodynamics technically does not apply to non-equilibrium systems. At least much of thermodynamics concerns itself as equilibriums, and so it does not apply over there. The Daniell cell is not reversible, so strictly thermodynamics doesn't apply. Practically, it's so slow for the ions to go to that if you don't really push them hard by voltage, you don't have much of a problem. Rechargeable batteries are reversible. Now I would like for a moment longer to talk a little bit about why it is so great working with electrochemistry. And that requires me to go on the board again. Think about it. When is a battery flat? Battery is flat when it doesn't offer you any voltage anymore. Okay, so my delta V is 0. When the battery is flat, my delta V is 0. You all know that. What does it mean, thermodynamically? Thermodynamically, it means this battery finally found equilibrium. Before that, the battery was in the state, I wish I could go flat, I wish I could find equilibrium, but there's not enough load around where I can push my electrons through, and so I need to be in the state where of a hole. But at some point, the battery will have found enough load where it can drive its electrons through, and ultimately it will get into equilibrium, the point where it doesn't offer to do any work anymore. That is really the definition of equilibrium. So, if I have a Daniell cell, that what that equilibrium means, and maybe I should cure, then I have this reaction of copper 2 plus 2 electrons becomes copper, and I have this reaction of zinc getting zinc 2 plus 2 electrons. I have an equilibrium between those two reactions. And I can add them up, of course, and the overall reaction I have in this cell is in the Daniell cell is that copper ions plus zinc makes zinc ions plus copper. So I have an equilibrium between them. Then I, of course, can define an equilibrium constant K, and that is the concentrations of the products, concentration of the zinc 2 plus, concentration of copper, I don't need to worry about elements, standard state, solid anyway, no concentration, forget about it. And then concentration of reactants, copper 2 plus, and again about the zinc, I don't need to worry. So this K over here, I have an equilibrium constant for that reaction. Now what will that equilibrium constant be? Now that is determined by this battery is flat. When the battery is flat, we have an equilibrium concentration. When the system is in equilibrium, the battery is flat, I am at the equilibrium concentration K. So this 0 over here is also this V0, the standard delta V0 of this Daniell cell plus RT over minus NF times the logarithm of the product over I over the activity to the stoichiometric coefficients, correct? So, if I want to figure out this one here, and this one here is of course that one. That's the same thing. So this is also an equilibrium delta V plus RT over minus NF times the logarithm of K. Because this product of the activity, that's exactly what I would like. So if I know the two voltages over here for this reaction, if I know over here for what is the standard potential for copper and what is the standard potential for zinc reduction, then my 0 being this one here that is the standard for the copper 2 plus 2e minus, making copper minus the standard for zinc 2 plus 2 electrons, making zinc. And then I have R minus RT over F, the logarithm of K. So, K. So I can bring that on the other side and then say, okay, Ln K equals F over RT times this delta V0. Right? So from my standard potentials, I can immediately obtain, if I have my standard potentials like here, I immediately can figure out what is the equilibrium constant for that reaction. Is it important? Now, if you were to measure, if you were to access out a value which you were getting for that equilibrium constant is quite astronomical, 1.68 times 10 to the power of 37. That's equals K. So if you put e to the power, then here it kind of explodes. Okay. So this corresponds then, of course, to concentrations which are so small of the copper ions that you will never able to measure them. So you can determine from the voltage here concentrations of copper, which would be 1 over 37, and that would be 1 over here. So ridiculously small, unphysically small maybe. You would be able to, you are able to determine those concentrations from the voltages, even though you could never titrate or measure them in any other way. So equilibrium constants are not measured in reality by titration of something. They are measured electromagnetically. You just get voltages, you have it. So again, electrochemistry saves you lots of conventional chemistry lab work. Goes on why it's so nice. The next thing is you might be interested not only what the delta G is of your reaction. You know already the delta G of your reaction, you are getting right away by minus NF times the voltage, correct, of that reaction. But you might also be interested for a reaction, what is delta S? Change in entropy under standard condition for a reaction. How can you get that? Now, in thermodynamics, you should have, I don't know whether you did, but you should have derived an equation that the change of the Gibbs free energy with temperature at constant pressure, that is the same as the negative of the change of the entropy. Now, either you believe me or you remember that equation from your thermodynamics class, whichever way it is. This here, the delta G, is of course minus NF times the V of that reaction, the voltage of the standard conditions of that reaction. Okay, so I'll put this in. I'll put something with a minus sign in here, and I have another minus sign over there, so they cancel. So I have my delta S equals then d of d0 by dt, and the N and the F, they are constants, they are not affected by the temperature. The N being 1 over here is not number of moles, the N is how many electrons are being transferred, 1 or 2 electrons. Right? So, times N and F. So, if you want to know what is the entropy change in the reaction, which we just looked at, we look at the Daniel cell again, if you wish. If you look at the Daniel cell back, I think it was like here. What is the change of entropy if I dissolve the zinc ions and take the copper ions out of the solution? Is there more or less entropy as a consequence of that? Then what we can find is this change in entropy associated with the reaction of dissolving the zinc, taking the copper out of solution, that is given by the slope. How does the voltage of that cell change with temperature? Meaning that if the Daniel cell has a constant voltage and temperature, make it a little bit warmer, put the solution maybe to 30 degrees centigrade, which would be somewhere like 80 Fahrenheit or so, or you put the solution to 10 degrees centigrade, which might be like 50 Fahrenheit or so, and you have the same voltage of your Daniel cell, then you know not much change in entropy going on. But if you find that the voltage of the Daniel cell changes a lot as you vary the temperature, then you know there's lots of entropy change associated with that. And that entropy change can be positive or negative. There are cells which have a positive and other cells which have a negative entropy change associated with their reaction. Something which slopes up and something which slopes down. Now if you want to do that practically, what you do is that I'm having here sample values over here, plotted over here, you plot them out. Now you measure them, and because you measure them, it will not look really super smooth over here, because you don't measure infinitely precisely. You know that in the lab. Your measurements aren't always precise, might not be. But they are somewhere scattered around. So what you do is you try to fit your data for that. You put your data into Excel or any other program which allows you to fit it, and you use a second order or a third order polynomial in order to fit your data. That is, you go into the fit function dialog box in Excel, you say polynomial, you say second or third order polynomial, and you click that you want to have the equation displayed on the chart. Don't forget it, otherwise it just shows you a line of the equation. And then you get this equation over here for the voltage as a function of temperature. If temperature is on the x-axis and voltage of the cell is on the y. Okay, now you have this function. This is now a polynomial, and for a polynomial, you know how to make a first derivative, correct? For a polynomial, you know how to calculate what is the first derivative of the voltage by the temperature. For a polynomial, okay, this here is power to the 3, so it's 3 times squared, the 3 goes in front of it, and so on and so forth. Okay? I hope that makes this clear. You also have sometimes a problem that with this one over here, and how much precision you're going to display. And you need to then click in Excel that you want to have this one here with enough digits. So you right-click on this one, and then format, and then scientific, and then how many digits. So that you're not getting just an 8 over here, but that you're getting a few more digits for that 8 that you can do your mouse power with. Okay, then you get your result. And that is what you can, that formula which you're getting over there, this formula of y being v and x being t, that formula you're plugging in here. And that way you can do your first derivative. That's what we are at constant pressure. Here pressure doesn't change without writing a cell phone automatically, so constant pressure will be there. Now, the beauty of electrochemistry goes on. It's not limited only to delta S. Of course, once you have delta S, you know you have a thermodynamics class. Delta G is delta H minus, if I have it right, yes, T times delta S. So, the enthalpy of your reaction. You know delta G, because delta G you get directly from the voltage. You know T, the temperature. You know delta S. So, you have everything you need in order to realize what delta H is. So, delta H equals delta G plus T times delta S. If you calculate what delta S is, you can measure what is the reaction enthalpy for this reaction of copper being precipitated, zinc being dissolved. Without doing any calorimetry. You just need to read voltages on your meter as a function of the temperature of your solution, that easy. Astonishingly, it goes on. Now, the next thing you might be interested, what is the change in the heat capacity of your system as a function of that reaction? Heat capacity at constant pressure. And the heat capacity of constant pressure is, as you probably still remember, T times ds by dt at constant pressure. Okay, so if that is the case, then this is T times, and this delta S was already dV, so d squared V0 by dt squared, still at constant pressure. So you just make the second derivative of this function over here, and you know what the change of the heat capacity of your battery is in consequence of having the Daniels-Tau reaction, or whatever reaction you're looking to proceed. Because you use a second derivative here on the side, because you use a second derivative, you can't have a straight line fit. You can't have a linear fit as Excel will want to do it. You can't have a first order polynomial because the second derivative of the first order polynomial is 0. So you need to have a second or third order polynomial in order that you can make in a meaningful way the second derivative if you want to go all the way to the details. Makes sense? Okay, that is really all which I had for today. Then there's a homework. In the homework, I'm assigning you two aspects. One aspect is do these calculations of the derivatives. I'm giving you here values for the Daniels-Tau, which is over from the internet, and you find them, get results there. Then please calculate those values. And then the first part is the question, how do you measure a standard potential? And measuring the standard potential is not as easy as just putting the electrode in and measuring with a multimeter, because of those activities and activity coefficients. If you like to use the Atkins book in section 61A, it describes on the whole page what you have to do. If you like to use the Levine book, there is a section called Determination of this round E with a 0. You can read it up there. What your homework is, read it, understand it, and reproduce it in your own words what you need to do. That is really what it is. Okay? Any questions? Then I guess I'll see you.